we will discuss high electron mobility transistor or HEMT. There are various names of high electron mobility transistor. Like it can also be represented by HEMT, or MOSFET, or we can say AC. Now, HEMT means two-dimensional electron gas field effect transistor. MOSFET means modulation doped field effect transistor, and ACFET means selectively doped field effect transistor. We will come to all these points why the name is given. So at first we have to understand the basic construction of HEMT. So it is very much similar to our normally MOSFET, which is metal oxide semiconductor field effect transistor, in which it also have source, drain and gate. Only difference lies here that beside or under the gate there is some heterojunction formed between two different semiconductors. What are these? Aluminum gallium arsenide and gallium arsenide. Provided here X must be 0.25 so that the band gap energy becomes approximately 1.73 electron volt, and for gallium arsenide the band gap is nearly about 1.42 electron volt. So we have to construct some heterojunction between these two types of semiconductor. Why? Because in our normal MOSFET, we have similar types of semiconductor, so that our frequency response is not so good. Frequency response means by the change of small amount of frequency, how quickly the device responds. So here our intention is to increase the mobility of the electrons and to increase the frequency response of the device. And to quick switching action, we have to improve the quick switching action of the device. That's why we have opted the different kinds of semiconducting junction beneath the gate. So here under this is N-type aluminum gallium arsenide. I have not written here the composition. The composition is given at the right hand side. Now, here another layer is present, which is undoped aluminum gallium arsenide. Under this, there is undoped gallium arsenide, and under this semi-insulating gallium arsenide substrate. Okay, so this is the basic construction of the HEMT. But here I have not represented one layer, which you will come to the point after a little bit. So let us see the band diagram. I have already mentioned at the right hand side what is the energy gap associated with this kind of two different semiconductors. One is gallium arsenide, which is having a high energy gap, near about 1.73, and another is small energy gap, which is like this. This is gallium arsenide. we will see when we draw the Venn diagram what is the difference between them. So this was the before contact. Now after making the contact, let us mention some point. Here onto the source metallic contact is made, which is ohmic, and at the drain metallic contact is also made, which is also ohmic. But here at the gate we have to make Schottky contact. And these are ohmic contact. Now let us discuss the band diagram. So after making the contact, this is the formula. This is the meter. This is the thickness associated with N-type aluminum layer arsenide. And this is the thickness associated with the undoped aluminum layer arsenide, or it is also known as spacer. So we have to see the energy difference. This is the barrier energy associated with the metal, beyond which it can donate the electron towards the aluminum gallium arsenide. And this is the conduction band difference, which originates due to the two different kinds of semiconductor. We have made the heterojunction here, so that the discontinuity in the conduction band is observed. And this is the pinch off voltage. So this is our energy band diagram associated with the thickness. Now so we have seen the construction of the HEMT. Now we will discuss the working principle. So one of the key parameters for the operation of HEMT is Vp, which is known as the threshold voltage, which we apply at the gate junction. So when we apply a negative potential at the gate, which is the minimal value of Vt, then there some inversion there or some charge field concentration generates, which we call as the two-dimensional electron gas. That's why the name two-dimensional electron gas, high electron mobility constant is given. So this is the two-dimensional electron gas. So here we have represented this. Why this bend like this? Because of the elimination of positive charge by the application of the negative voltage at the gate. And at the same time, there is some negative charges generated, which tends the band to lies at there, and the lower portion of the conduction band of the undoped gallium arsenide merge with the Fermi level here. And here some potential will generated due to the application of this negative voltage at the gate junction. So we can say that the device is on. Now as we increase the negative voltage here, more the voltage which is ranging from 0 to the drain voltage V. So here, so ESY has been represented by the area concentration which is generated here. And now when we apply some voltage here, it will help to induce the electron here from here, so that the conduction will be easier and the device will be quickly response to the change of the frequency, which is our aim. Now the expression lies here. This will be Q naught V, and we have earlier known that this is 5 here. This was Vp and this was delta AC. So from here we can read the expression of Vp as 5 minus delta AC by